Good morning to all. Today I am going to discuss a very important problem of the quantum mechanics, that is the motion of the free particle in a box. Basically, in this lecture, I am going to explore the conceptual understanding and application of the Schrodinger wave equation. And this problem is also very important in the future study. This has a lot of application in the field of the semiconductor, where we try to calculate the density of a state, and it is also applicable in case of the nanotechnology, study of the nano systems. So first of all, I would like to discuss the what is this problem. Now let us start. A free particle in a box. Let us consider a quantum mechanical particle of a mass m. It is freely moving along the x-axis in the region of 0 to a. A is the size of the box, and whereas the particle is considered free, so that's why its potential in that particular region is 0. Beyond this region, let's say x less than 0 and x greater than a, the effective potential is infinite. So for this problem, the potential of the problem can be stated as in equation 1. That says that the potential, that is Vx, is 0 in the range of 0 to a, whereas it is infinity beyond this range, or you can say otherwise it should be 0. Remember, as we know, the a quantum particle which is moving, it means there is a wave packet associated to it. So that's why we try to solve this problem with the help of the Schrodinger wave equation, whose solution can form the corresponding wave packet which is associated to this free particle. Let us consider the certain points here. The motion of the quantum particle of mass m in a given region 0 to a is described by the Schrodinger wave equation. Let's say this is the box of the length a. It is having motion only along the x-axis. So this particle is moving towards this wall, one of the end of the box, and it is returning back from this wall towards the other wall, which is situated at x is equal to 0. and in between the two wall along the x-axis situated at x is equal to 0 and x is equal to a, the particle is freely moving, means the potential inside must be 0. But outside this box, the potential is very large, or you can say infinite. Therefore, it returned back to the in this box from these walls. Therefore, we try to solve the problem. Let us consider the plot of the potential function. At x is equal to 0, the potential is to be set to be infinite. Beyond this, it is to be infinite. At x is equal to a, that's the potential is again infinite. But between the x is equal to 0 to a, the potential is always be 0. So this is the potential which is 0. Now, applying the Schrodinger wave equation, so the time independent part of the Schrodinger wave equation in general written as, that is the, you can say, the h cross square over 2m second order derivative of psi x plus e minus vx bracket close psi of x is equal to 0. But the particle exists only the region between the x is equal to 0 to a, where the potential function is 0. So equation 1 can become the second order derivative of psi x with respect to x plus 2 em over h cross square psi x is equal to 0, that is equation 3, where we consider a alpha is square is equal to 2me over h cross square, that is equation 4. So substituting the value of alpha square in the equation 2, we get a equation, equation 3, we get a second order derivative of the psi x plus alpha square psi x must be equal to 0. To solve this equation, we have an auxiliary equation m square plus minus alpha square is equal to 0, where auxiliary solution is psi x is equal to, or you can say directly proportional to the e raised to the power mx. This is the auxiliary solution, or you can say this is the trial solution of the problem. Let's substitute this trial solution in the equation 5. We get equation that is m square plus alpha square is equal to 0, which resulted from the substituting this value into equation 5. We get the m square plus alpha square into psi of x goes to 0, where psi x cannot be 0. Therefore, the bracket entity m square plus alpha square equals to 0, and this equation is called the auxiliary equation, where m can have the two possible solutions plus minus I alpha. So m1 is plus I alpha, m2 is minus I alpha. Therefore, the general solution of the equation 5 is given as psi x equals to a times of e raised to the power I alpha x plus b e raised to the power minus I alpha x. Let's say this is 6, where a and b are arbitrary constants. Let's try to calculate them by using the boundary condition. So what are the boundary condition? The first of all, you think about that the particle reaches at x is equal to 0 at and x is equal to a, the particle should not exist at these boundary. Therefore, the corresponding wave function must be 0. So that's why the first boundary condition equal BC1 is psi at x is equal to 0 must be 0, that is 7a, and BC second boundary condition second, psi at a equals to 0, that is 7b. Now substituting these values in the solution 6, we get a is equal to minus b. So one of the parameter, that is 7c, one of the parameter is eliminated, and we have the equation 7 as a solution. Psi x equals to a star sine of alpha a, where a star is 2ia. Now going further and using the second boundary condition x is equal to a, at x is equal to a, psi a also goes to 0, where a star sine alpha a must be 0, a dash should not be 0. If we consider a dash equal to 0, then no solution exists. Therefore, the sine alpha a must be 0. And solving, so alpha a has the value plus minus n pi, where n can run from the 0, 1, 2, 3, but n could not be taken 0 because it has it always be for every x has wave function is 0. So it is a trial, so it is a trivial solution. So that's why it is not under the consideration. Therefore, n could not be 0. So the general solution of the problem become psi star, sorry, psi of x is equal to a star sine of alpha x, where alpha is n pi by a. So a star sine n pi by a times of x, where n can run from the 1, 2, 3, 4, 5, 6 and so on. Now the equation 8 and equation 4 give us a very outstanding result, where equation 4 says alpha square is equal to 2m e over h cross square, and we have also alpha is equal to, from equation 8, alpha is equal to plus minus n pi by a, where n can run from the 1, 2, 3, 4. Substituting the values of alpha, and so we get a energy expression, that is En is equal to n square h square 8m a square. So I can rewrite this in term of a compact representation. En is equal to n square times of epsilon, where epsilon is taken as the n square over 8m a square, and n can run from the 1, 2, 3. Please see this, sorry. Once again you look at that, this is a very interesting result, and I would like to say that the equation 10, which is a specific expression for the energy, which is which gives the allowed energy of the free particle, and that is discrete in nature. If we plot graphically for the n is equal to 1, n is equal to 2, and n is equal to 3, we get the certain graphical representation. Remember, in this problem, n could, the lowest value of the n should be 1. So we have a corresponding state or a level that is known as the ground state. So n is equal to 0 is never be taken as the ground state. You always remember the n is equal to 1 is the ground state for the problem. So that's why this equation is also known as the equation 10 is also known as the eigenvalue of the energies. For this lecture, it is I'm enclosing the lecture here, and I will start from here in the next lecture. Thank you to all.